Okay, so today we are now starting new material that will be towards exam 2. So today and Wednesday is the next round of stuff. Today and Wednesday you're turning in the last quizzes that the exam will be made up of. So Wednesday's class we will do some reviewing for the exam. And the exam is on Friday. Several of you have indicated that you want to take your exam Thursday morning. Absolutely fine, doesn't make any difference. I want to make sure, though, if you're not going to take the exam on Friday, don't leave today without double checking and reaffirming, and so I want to get all the logistics correct. I don't want anybody kind of dangling in the wind. Different little scenarios. We will review on Wednesday, and so technically any time after that is certainly fair game, although I don't think any of you wants to take an exam minutes after class on Wednesday. I think that would not be in your best interest. I think you still want that little extra time to, double check, go over the last few things. Remember, the exam covers the material we finished last week, so you still have way over a week of preparation. Now today we're going to do something that it's a little bit different, and at first it doesn't seem like it has a lot of application, yet it really, really does. So I'm going to ask you a question. If everyone can pull out their calculators right now, everyone who has a calculator, you guys know what factorials are, right?
Yeah.
So if I asked you to do, let's say, 10 factorial on your calculator, so tell me what you get.
3,628,800.
Okay. If I asked you to do, let's say, 30 factorial on your calculator, now all of a sudden your screen looks a bit different now, doesn't it? It's giving you kind of a weird looking answer. What does it look like now?
2.6525289 times 10 to the 32.
Yeah, it gave you a scientific notation answer. How come?
That's too big.
Because it's too big. Yeah, that means this thing's 32 digits long, and nobody has a calculator screen that's going to show, I don't know, maybe you do, get wrap around. Is it practical to have all 32 digits, or is that more useful, just knowing it's on the order of 10 to the 32nd? But that's huge. Factorials are the fastest growing things that we have. In Calc 2, you're going to spend a significant amount of time working with these. Now, how about 69 factorial?
1.7112245 times 10 to the 98.
Now, one thing we do know about factorials. If I said 10 factorial, does that equal 10 times 9 factorial? Is that true?
Yeah.
And, just for fun, 10 times 9 times 8. These are ways I could do it if I didn't have a good calculator. So 70 factorial is obviously 70 times 69 factorial. So it's 70 times that first number, which is about, 70 times this number here is about 120. So that would make this approximately 1.2 times 10 to the 100. So just for fun, do 70 factorial on your calculator. And your calculator says probably what?
Overflow error.
Overflow error. Did you do something wrong? It gave you this one, but it didn't give you this one. What do you suppose the overflow error is? Well, I have a TI 89 titanium. I can go up to 449 factorial on mine, because I will go up to 10 to the 999th power, and then it craps out and says overflow error. It said overflow error because your calculator won't store anything bigger than 10 to the 99th power, and this is now on the order of 10 to the 100th. Would you say that's a big number?
Yes.
Would you say 70 is a big number compared to infinities? No. 70 is pretty wimpy. What if you needed 1,000 factorial? What if you needed 1,000,000 factorial? What if you needed an astronomical large number factorial? There's no technology on planet Earth that can do that. The numbers are too big. But what if I actually need a value? You see where 70 factorial is not a very big number, yet our calculators can't even handle that. But what if, just for fun, how many here have ever written any computer code? We got a problem?
They're trying to figure out how to find factorial on
Yeah, you got to go to the math menu and then all that kind of stuff. Don't worry about that now. I'm giving you an example, okay? If I use logarithms, don't we know this is true? So what if I actually needed a value? I really did need a value, and it was bigger than my calculator could do. Turns out I could use logarithms to help me get it. This is exactly how it's done. This is exactly how a computer will do it when the number is large. So if I wanted to do, I'll just do a small one, like 5 factorial. If I said I want the logarithm of 5 factorial, well, isn't that the log of 5 times 4 times 3 times 2 times 1?
Yes.
But the log of a product is the sum of the logs. Now do that for me on your calculator. Add up those numbers. The last one, by the way, is 0. So add those numbers. It's a really cool application of logarithms that we're going to show today. It doesn't even necessarily have to involve calculus. So when you added up these numbers, what do you see on your screen?
0.89.
So Mickey decimal. Now, I want 5 factorial. So I'm going to need to go e raised to this power, aren't I? Tell me, is this true? We started this last day. Is this true?
Yes.
So you have a number on your screen. I want you to do this. Go e raised to, and my favorite key is the answer key. The answer key is whatever you had on your screen a moment ago. Go e raised to the answer key. And what do you get?
120.
Should get exactly 120. Should get exactly 120 because you just did e to this, you got back 5 factorial, which is 120. So what if I wanted to do a really large factorial? Now I said, how many have ever written any basic computer code? Anything, a do loop. You understand a do loop. For I equal 1 to 1,000 do. Add log I. So you add log 1 plus log 2 plus log 3 plus log 4 all the way up to log 1,000. You're essentially finding the log of 1,000 factorial, which means you just found the exponent. So no matter what your exponent is, your final answer would be e raised to that power, and all computers could store that because exponents aren't big. E raised to the exponent is a big thing. Now think about that for a moment. So if I wanted to do, just for fun, biggest number I know of is a bazillion. That's the biggest number there is, I'm pretty sure. I want to do a bazillion factorial. So it's a bazillion times a bazillion minus 1 times a bazillion minus 2. On and on and on and on, 3, 2, 1. Well, if bazillion is bigger than 69, I probably can't even do it on my calculator, but I want to do it for an astronomically large number. So what I do is I get my basic do loop. I don't do this by hand. Are you crazy? I did this by hand because I had to do 1 to 5. What if we wanted to do 1 to 100? Would we do that by hand? No, we'd write a simple computer program. That's what people do. So if I wanted the log of this, then based on what I just said, it would be each number added. So it would be the log of bazillion plus the log of bazillion minus 1, which is still pretty darn big, by the way. And how many times would I do this?
Bazillion times.
Dot, 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 down to log 3 plus log 2 plus log 1. This is a constant. Do you agree? And by the way, because it's an exponent, it's not nearly as big as you think it would be. Just for fun, let's take a big number. Give me a big number, huge number.
1,000,000.
1,000,000, okay. 1,000,000 is pretty darn big. We all agree. Now, take the log of 1,000,000. What does your calculator say? Do the log of 1,000,000.
13.81551.
13.8 something?
Yeah.
That all of a sudden is not so big and scary, is it? That's kind of wimpy. Well, a billion, a trillion, a bazillion. No, that number's not very big. Not the log of it. Because you're telling me the exponent. Oh, so if I raised e to this power, I get back the million. So let's give this an answer. Let's just call this number, I don't know, how about A for awesome. You did this, not by hand. You wrote a computer program to just say, for I equal 1 to a bazillion do, add log 1 plus log 2 plus log 3 plus log 4. I don't care how big that number is. If you do this on a computer, this is taking seconds, isn't it? This is not taking hours. This is taking seconds. Now you have some really, really big number in front of you. Can you now tell me the value of bazillion? factorial? Yeah. It's e raised to this power. Isn't that what we just did here? Isn't that crazy? But at the same time, isn't that absolutely cool? You can calculate astronomically large numbers that are beyond what any human being can ever do with any technology 1,000 years from today. This is so far beyond the limit. The limits of technology are actually pretty weak. The supercomputer at UCSD can't even talk about 1,000 factorial, let alone. But that 1,000 is not a big number unless we do something like this. Now I can go as big as you want. But I'm using logarithms kind of to get me there. I'm using the fact that logarithms have these properties that the log of a product is the sum of the logs. Now what I want to do is employ this in some of the calculus that we already know. Not the logs we did last day, but actually stuff we did before then. And so I'm going to introduce something to you called logarithmic differentiation. Now essentially what this means is I have something that does not involve logarithms. There's no logarithms in the statement. Last day we learned how to differentiate things involving logarithms, and there's some really simple and really cool rules. I want to talk about things that don't have anything to do with logarithms today, and I want to introduce logarithms as the way of making the problem work. So let me start with something really simple. Okay, let's suppose y equals f of x. And I want to find dy dx. Well, we know what the answer is. It's going to be f prime of x. But I want to do it using logarithms. I'm going to show you a really roundabout way. This is not efficient. It's just another way of looking at it. So the first thing we're going to do is we're going to do some Trig-ish stuff now. Going to go into our Wayback Machines and look at some things. So I want to go even further back. And we want to talk about, just for a moment, inverse functions in general. Some of the rules and regulations. Now, if you can write anything, an equation at all, it has, I'm talking about from a graphing standpoint, x and y, it's going to have an inverse. But inverses are not always functions. So let's start with a really simple one. If I started with y equal x squared, now we know what that looks like. That's pretty easy, right? It's a simple parabola, because that's a terrible parabola. Let me do this one more time. That's my next one, not this one. I want to do y equal x squared. Let me go way up high. Okay. And then its inverse would be x equal y squared. I'll use a different color, which would be this one. Anything that you can write down to get the inverse, all you do is swap the roles of x and y. Because the definition of the inverse is input becomes output, output becomes input. We all agree that the parabola y equal x squared is a function. But is the parabola x equal y squared a function? Why not? Yeah, because I have many, many, many x values that give me different outputs. Right? And that violates the function. A function, each input has a unique output, and the sideways parabola is not the case. So why did that fail? Well, let's draw another graph. What if I have a graph, and let's keep it really simple, something like y equal x cubed. This is a nice, happy graph. Well, if I swap the roles of x and y, I have the cube root function, which essentially looks like this. Okay, so this is y equals cube root of x. This is y equal x cubed. Is the cube root function, is the cube root a function?
Mm-hmm.
Yes.
So when I did y equal x squared, that's a function, but its inverse was not. Here, y equal x cubed is a function, and its inverse also is a function. Is there a big difference? Now, why did it fail? What were the words you used? It failed.
More than one y.
Yeah, but that's not the term. You said something about.
Vertical line.
Yeah, remember from kids in algebra. If it is possible for me to draw a vertical line that passes through more than one point, it's not a function. Because that means one input gives me multiple outputs. But y equal x squared is fine. Its inverse failed the vertical line test because the original function failed a horizontal line test. A horizontal line test isn't a test to see whether something's a function, it's something else. It's a test to see whether something's what's called one-to-one, and that's the key. Some of you may remember that term. One-to-one. Okay, first of all, we're starting with a function. That means each input has a unique output. One-to-one means each output comes from a unique input. If I go to the number 9 here, aren't there two different inputs that gave me the number 9?
Yes.
If I input a 3 or a negative 3, I get a 9. So although it is a function, each output did not necessarily come from a unique input. It didn't work in reverse. In other words, I can't go backwards. What number when I squared is 9? You have two possibilities. I'd really rather only have one. So if my function fails a horizontal line test, then its inverse will fail the vertical line test. Everything has an inverse, not every inverse is a function. Did the cubic graph pass a horizontal line test? Yes, and so therefore its inverse passed the vertical, because all I'm doing is flipping basically over the line y equal x. So if a function is one-to-one, then we say the function is monotonic. You may want to take a stab at what that might mean. Well, what's mono? One. Monotonic. It's always going uphill or it's always going downhill means it's going in one direction. That's it. A monotonic function is always going uphill or it's always going downhill. It does not turn around. So a function has to be monotonic in order for the inverse to also be a function. That's absolute across the board. So what if your function's not monotonic? Then how in the world do I find an inverse? Well, then we do something that, again, some of you may remember this. If I talk about y equal, I'll put it up here, y equal x squared, what is the domain and the range? Maybe I'll use it here. Y equal x squared only. What's the domain? All reals, and the range is?
Positive? Zero?
How about 0 to infinity? Yeah, non-negative actually would be how we'd say it. Okay? Now, let's look at the inverse, which is x equal y squared. What's the domain of this one? This is an absolute across the board for everything that exists. When you do the inverse, tell me about your domain and range. Yeah. It's not an inverse if they don't just simply switch places. So you don't actually have to think, what's your domain? 0 to infinity, your range. By the way, if you did not learn this in remedial algebra, probably pre-algebra, somebody did you a disservice because you use this pre-algebra, elementary, intermediate, trig, pre-calculus. Inverse comes up in every one of those classes and it gets bigger and bolder in each one. You do the inverse trigs and trig and you do inverse of everything else in pre-calc. But this is an important one. We need to know this one. Domain and range simply switch places. Let's go back to here. Y equal x squared is not monotonic, but is maybe half of it monotonic? Which half do you would you want to use? Maybe everything to the right of the origin? So just for the heck of it, I'm going to erase this, and I'm only going to use this, which means I'm only going to use this. This is what is called restricting the domain. I'm going to use less domain. Is the portion of the domain I used going to make this monotonic?
Yes.
Now, what's going to happen to my inverse when I do that?
It's going to exist.
It's going to be that, isn't it?
Yes.
When I restricted the domain of the original, then I'm also restricting the range of the new one. Now, by the way, when I restricted the domain, did I change the range at all?
No.
No. So it's very important that I restrict it in such a way that I don't lose any of my range. Now look at that picture. Is my original function now monotonic? Is its inverse now a function?
Yes.
And what is that inverse called?
F.
Very specifically? square root function. Ooh, that's the square root function. When I take the square root of a number, I don't generally get two values back, do I? I just get the one. Oh, so the square root function is defined from the y equal x squared if I restrict the domain. So if I take something that's a function and I restrict the domain if I had to make it monotonic, then its inverse is automatically a function. So why am I doing that? Because now we need to do this for all of the trig functions, which you have done in your life. You just haven't done it, well, recently. Okay, so let's start with something. Let's start with y equals the sine function. My pens are all sort of dying here. All right. Do we agree this goes forever and ever in both directions?
Yes.
Okay. This is clearly a function. Is its inverse going to be a function? No, its inverse is going to zigzag along the y-axis. Here's the problem with this, okay? The sine of pi over 6 is equal to, this is a common one. Use your calculator if you want.
Never 2 over 3.
No, it's easier now.
This is 1 over 2.
Yeah, it's a half. Yeah. The common angles are good to know because they come up often. So if I were to draw a unit circle, let's say, I know that point is root 3 over 2 comma 1/2. I know that. So the cosine of that angle I know is root 3 over 2. That's all right? So what's the answer?
Over 6.
Is the answer pi over 6? Well, certainly that works. But what about pi over 6 plus 2 pi? What about pi over 6 plus 242 pi's? How many times can I go around the circle and end up there?
As many as you want.
As many times as I want. So how many different representations are there of this position? Infinitely many. They're called coterminal angles. Ooh, so I wouldn't say pi over 6. I'd say probably pi over 6 plus like 2k pi. While we're at it, isn't the sine of 5 pi over 6 also 1/2? Oh my God, there's not only infinitely many answers to this question, there's also 2 places on the circle I could be. You see the dilemma we have here. So, I really would like to get pi over 6 back again though. I would really like to ask the question in such a way that the only answer you gave me was pi over 6, not infinitely many coterminal angles. In other words, go back to the original parabola. The very fact that I got more than one answer when I asked what gave me this number, when we restricted the domain. Could I restrict the domain of the sine function?
Yeah.
Well, right now, do you agree that domain is all real numbers for the sine function?
Mm-hmm.
There's no restrictions on the domain, and right now, what is the range? We're going to take the natural log of both sides. Okay? So now I can say with certainty that the natural log of y equals the natural log of f of x, as long as this is positive. Now I want to differentiate both sides with respect to x, so y is a function. So if I differentiate both sides with respect to x, we write it this way. We say d dx both sides. So in English, that means differentiate both sides with respect to x. So I'm going to go d dx of log y equals d dx of log f of x. Now, we learned last day the derivative of the log of a function is 1 over the function times the derivative of the function. And so the derivative would simply be dy dx. That's the left side. The right side, well, same thing. 1 over the function times the derivative of the function. Okay? Now, I wanted to know what is dy dx. I have this extra term floating around over here. So could I multiply both sides of this by y?
Yes.
Would that be a legal move?
Yes.
Yeah, if I multiply both sides by y, now I have dy dx equals y times 1 over f of x times f prime of x. Which makes it really nice because how did we start the problem? Is that the result we needed to get in the first place? These guys cancel because they're the same thing. Now, was this the most roundabout way of ever taking a simple derivative? Yes, it was. But if I do this, it turns out there's a lot of problems that could be really complicated that we might be able to make really simple. Now, I'm going to start with something really simple, like product rule. I'm going to revisit product rule. Now, we don't have any question on product rule, and in general, that's not something that's going to usually give us much of an issue. Y equals, let's say, we'll keep it simple, f of x times g of x. All right? That's what y equals. We can put anything in there we want. I want to use the logarithmic differentiation, which means there's no logarithm associated with the question. I'm going to take the log of both sides and then differentiate that new problem. And when I do that, I want to show you the steps along the way, because then we're going to do it for several different types of things. First thing we're going to do is take the log of both sides. Now, look at the right side for a moment. Can I do anything with that?
Yeah.
What can I do very specifically?
The product of logs is equal to the sum of the logs.
The log of the product
Oh, the log of the product
is equal to the sum of the logs. So is it true that this is log of f of x plus log of g of x?
Yes.
Now, what's easier to take the derivative of? F of x or f of x times g of x? Well, just f of x. Right? Differentiating a product is always way more work, but I don't have to differentiate a product anymore on the right side. Huh. All right, let's take the derivative of both sides. So on the left, just like we did before, I'm going to get 1 over y times dy dx. On the right-hand side, I'm going to get 1 over f of x times f prime of x. Can I be lazy and just put f prime in the numerator?
Yeah.
Yeah. Does anyone have a problem with that?
No.
See, I didn't do it here. I could have just put that in the numerator, couldn't I? And it probably reads a little easier. And what's the next term?
G prime x over g of x.
So far, so good. Now, I have a sum of two things. I really would rather that look like one quotient. I think it would be easier to work with later. How do I make that into one quotient? I need an orange pen to do that. Here we go. Well, let's see. Could I multiply by g of x over g of x here and f of x over f of x here? Is that legal if I do that?
Yeah.
Yeah.
Okay. Then on the right side, I would now have g of x f prime of x plus f of x g prime of x all over f of x times g prime of x. Okay. Now, I want dy dx all by itself. For me to get dy dx all by itself, I need to multiply both sides by y. Agreed? So it'd be y times all of this stuff. All right. Oh, by the way, what does y equal?
That.
Are these going to cancel? Yes? No? Maybe?
Yeah.
Oh, and what am I left with?
Product.
That looks like the product rule to me. Huh. Well, it would have been way faster just doing the product rule. You're right. You're right, it would have. This time. I think you're going to like this one a little bit better. Remember doing this one? I think this was on your quiz you just got back. Didn't we have a problem like this? We found the derivative?
Yes.
There was a lot of algebra. It wasn't hard algebra, but we agreed there was a lot of algebra.
Yes.
What if I do the logarithmic thing on this one? I'll just write it like this. Now, why would I do such a crazy thing? Well, the first thing, this is log of a product, so that's going to be so far so good. Oh, but it gets better. Abominable snowman, you guys see him?
Mm-hmm.
Remember, he lives in the exponent. What's he gonna do?
Bounce.
And his buddy? Huh. So now the right side is 3 log of something simple plus 4 log of something simple. And all of this, by the way, is equal to the log of y. I haven't done any calculus yet. I haven't taken a single derivative. I took the log of both sides and then I used log properties to simplify the right side. Now let's take a derivative. So when I differentiate the left side, it's going to be 1 over y dy dx. What's the right side going to be? Okay, this part I know. Is everybody okay with this? Those guys are going in the denominator. I have no question about that. So what goes in the numerator? What goes in the numerator here? What's the derivative of 4x minus 2? 4. What do I do with the 3? Oh, okay, how about 3 times 4? What's going in the numerator here? 6. But I had the 4, sir. I am completely finished with the calculus for this problem. There's no more derivatives. Now, I would prefer this be 1 quotient. I think it would be easier if I wrote this as 1 quotient. So in order for me to write this as 1 quotient, I need a common denominator first. So let's see, I think I need a 6x plus 3 over 6x plus 3 here. And here I think I need a 4x minus 2 over a 4x minus 2. Are we good on that?
Yeah.
Let's go ahead and distribute and gather terms. I think that's not too bad. So I have 12 times 6x plus 3, that would be 72x plus 36. Then I have 24 times 4x minus 2, I think that would be 96x minus 48. Okay, a little higher. So it looks like I have 168x minus 12 over this. Okay. And what does all that equal? That all equals 1 over y times dy dx. So just like before, I would like to say dy dx equals. So dy dx is going to equal that. Actually, let me give this a little more space. Multiplied by y. Agreed? But rather than write y, why don't I just take the original problem, which was that? Because that's what I'm going to end up doing anyway, right? I'm going to put that in there. So if I put that in there, then I have 4x minus 2, 6x plus 3 to the 3rd and 4th powers. All right, I'm done, right? Well, can I do a little canceling? What's going to cancel? Would you say all but one of them? How about here? All but one of them? Oh, that's it. Sorry. And that's exactly the answer we would have gotten if we had done it the way we did it before. Using the chain rule, factoring, gathering all the terms and all that kind of stuff. Same answer. But the algebra on this one was probably a lot less, wasn't it? Huh. Interesting problem. I got one more for you. You're gonna like this one. We're pretty good with product rule. I think as a group, product rule is not something we're gonna labor over. I think product rule is Is it negative 1 to 1 inclusive? So what I want to do is use, well, less of the number line without in any way messing with the range. I still need peak to peak. But I don't want to go back and forth. I don't want to turn around. So is there a portion I could choose that would cover all the y values without ever repeating anything? Yeah, maybe, I don't know, from about here to here? What do you think? And that's negative pi over 2. That's pi over 2. You notice I'm not saying 3 pi over 2. If I said what is this angle, we'd say 3 pi over 2. If I said backwards, we'd say negative pi over 2. They're both correct. But here, that's clearly negative, and that's clearly positive, because now I'm on the xy plane. So if I restrict the domain here to be just this, now when I ask for the inverse, will the inverse be a function? Yeah. And by the way, I don't need to know what the inverse looks like, but it's not very hard. I just take that graph and flip it. We're going to do this probably many times in calculus. So the inverse, I know what the sine wave looks like. The sine is doing that kind of thing, so the inverse is doing something like this. I have a horizontal tangent right here. So this should have a vertical tangent right here. This is my inverse. Well, in the case of y equal x squared, we said x equal y squared, but wouldn't it technically be y equals square root? Wasn't that its inverse? So I want to say y equals, not x equals. If y equals sine x, is it correct to say x equals sine y? Is that a correct statement mathematically? For here. Yeah, if I want the inverse. But I want the inverse to be a function. So this one, we write it like this. This is inverse sine. Anytime you have a negative 1 in an exponent position on a function, it always means inverse. In no context does it ever mean reciprocal. Ever. What's the only mistake people make? They use reciprocal, which means they get the wrong answer to every problem they will ever do the rest of their life when it's an inverse. An inverse is not a reciprocal. What's the inverse of a positive number? Is it its reciprocal? Is it its square root? Its square, its logarithm, its negative sign? Well, it depends what the operation is. Oh. So if I'm adding, the inverse is the additive identity. Which, if I'm exponentiating, the inverse is the logarithm, or the root, depending on which version I'm using. Inverse is not reciprocal, unless you're multiplying. Do people say reciprocal? All the time. No, in no situation. This is an absolute mathematical statement right here. You will never run into anything where this is a true statement, ever, in your entire lifetime. So don't do that. Don't do that. That no work. This is called the inverse sign. Now, let's go back to here. When I'm doing the sine function, what am I inputting? Sine of pi over 6. What am I inputting? What is pi over 6?
An angle.
It's an angle. What am I outputting?
A coordinate.
Okay? Or simply the ratio of something. It's a ratio. On the unit circle, it's the coordinate divided by 1, but if I'm not, think so katoa. Right? Isn't it so? Opposite over hypotenuse. In other words, the sine function gives you back the ratio of two sides. On the unit circle, it's the coordinate versus 1, which is why the unit circle is really helpful. I input an angle, I output a ratio. So what am I going to input in here?
The ratio.
Ratio, and I'm going to output the angle. So get out your calculators. I want you to do the inverse sine of 1/2. By the way, to make it easier, the answer to any question of this nature is always a radian answer. But if your calculator's in radian mode, tell me the problem with your answer right off the bat. It might be correct, but what's your answer going to look like?
Long decimal.
A decimal approximation of pi over 6, which of course you all have the first 10 or 12 digits memorized on pi over 6, right? Everybody knows that one. That's something you learned as kids, right? Or maybe no? Does any of you have fractional multiples of pi memorized in your head? So if I do this in radian mode, which is correct, I'm going to have an ugly decimal on my screen. How do I know if I did it right? Whenever you do an inverse trig function, do it in degree mode, and then change your answer to radians. So put your calculator in degree mode and do inverse sine of a half, and what does it say?
30.
30 degrees, which is pi over 6 radians. That's what I would do. Why? Because the answers are not always going to be common angles. But if the answer is a common angle, like 30 degrees, 30 degrees is pi over 6. That's an easy one. But what if it was, 37.3 degrees? Well, that's not a common angle. Then I'm not worried about it. Right now, it's just some icky decimal. So the inverse sine of this ratio produced exactly one angle, not all the coterminal angles, one angle. Which angle did it produce? The angle between here and here. So if I'm looking at a unit circle, inverse sine on the unit circle only produces angles on this side. First and fourth quadrants, but the fourth quadrant angles it produces are negative angles. So if I'm in the fourth quadrant, I'm not getting large angles, I'm getting small negative angles. Because again, going back to this picture, I'm getting negative to positive. So negative pi over 2 to positive pi over 2, okay? You have a calculator if you actually have to do the calculation, but understand what it is you're producing. Now, in general, we're not that concerned with inverse cosecants and inverse cotangents and inverse secants. We are concerned with inverse sines, cosines, and tangents because they come up a lot more. So let's do the same thing now with the cosine and the tangent function. Let's figure out where our restricted domain puts us. All right, so cosine function. Looks just like the sine function, only it's slid a bit. So it's almost the same graph, just slid over. So in this case, I need peak to peak. So I can certainly select this section or that section or that section or that section. This was easy. The peak to peak went right through the origin. That made my choice kind of a no-brainer. Do we want to include 0 in our answer? Probably. I mean, I don't want to go down here. Yeah. So should I include all the negatives or all positives? Do you think, to make our life easier? Probably the positives. So we agree. This is not some rule. We didn't solve the problem. We agree as a math community. We're going to take this portion because that will produce all the y values and it's monotonic. Well, that's pi. So if I take the cosine function and I restrict the domain to the closed interval 0 to pi, I'll still sweep out all the y values, but now I can define an inverse trig function that will produce one answer and one answer only. So this is how we determine the inverse cosine. So we do agree that the range here, just like the sine, is still -1 to 1. So now I want the inverse cosine of 1/2, let's say. So my calculator should produce an angle.
60 degrees.
So in degrees it's 60 degrees, so in radians it would be
1 over 3 pi.
5 over 3. So that wasn't that hard. Does this come up a lot in math? It comes up. I don't know if anything comes up specifically a lot, but what we're doing is way beyond the ability to calculate a number. We're using this for much, much bigger purposes than this, but we're reminding ourselves the whole point of an inverse is to produce a function that gives us back one answer, not multiple answers. We don't like that, okay? We don't like multiple routes because that might not be the same thing then. You might get different values. And finally, let's consider the tangent function. Now the tangent one is a little bit weird. There's my tangent function. Well, sort of. because there it is again. And there it is again. In fact, how many times does this show up?
Infinite.
Infinite. Oh, there's an infinite number of these guys, aren't there? Yikes. These are vertical asymptotes. That's at x equal pi over 2. That's at x equal negative pi over 2. So the tangent function, actually, my choice now is pretty easy. This is going from way down there to way up there. It never turns around anyway. But it does repeat itself. So I'm going to use this one right here because it's the only one that passes through the origin. So if we restrict our domain from negative pi over 2 to pi over 2, now it's open. If you do tangent of pi over 2 or tangent of 90 degrees on your calculator, it's going to say error because it's technically it's undefined. It's 1 divided by 0. I can do the tangent of 89.9999999 degrees. Right? And that's going to be very, very, very steep. But I can't do tangent of 90 degrees. So if I restrict the domain to this, tell me about the range of the tangent function. What's the range, you think?
Positive, negative,
All real.
negative.
So how about all reals? Negative infinity to positive infinity, exactly. All right, go back to inverse sine for a moment. Input inverse sine of 10. What does your calculator say?
Error,
Why does it say error?
because it's not a ratio.
Just it's an inverse sine of 10. The sine of what angle gives you 10?
Oh, see, I got a domain error too.
How come?
I don't know, there's a domain error.
Because didn't we say the sine function bounced between negative 1 and 1?
Yes.
Oh, so when I take the sine of an angle, can I get a value outside negative 1 to 1?
No.
Not really. Well, yeah, I can, but that's a couple weeks away. In other words, if I consider imaginary numbers and things. But I can't use a real number. There's no real answer to that question. There is a complex answer to that question. Something we're not going to label. What did I just do? I want the derivative of this. How would I do that? By the way, I can keep going. I can put more. How do I take the derivative of 3 functions in a product? Is it still product rule? What do you think? Would it still be product rule? Yeah, but what's my first function and what's my second function? So maybe we do something like this. Maybe we call f of x my first function, and we call g times h my second. Would that work?
Yeah.
Is this going to be a bit of work?
Yeah.
Oh yes, it is. So I'd say first times derivative of second, and then I got to use product rule in there. Second derivative of first. You agree that this one could be a little bit huge. Now, in theory, I didn't technically have to put these over a common denominator. We did because we wanted our answer in a factored form. I want to do the same problem, but I don't really want to do product rule multiple times. Oh, by the way, if you're okay with doing 3 functions, then let's do like 7 functions or 15 functions in a product. You got time, right? You got no plans for the rest of the year. What if I use logarithmic differentiation? You're going to like this because this is the reason we learn it, is for stuff like this. What if I do this? Now tell me about my right side. I have log of f times g times h. Isn't that log of f plus log of g plus log of h?
Yeah.
Are these individual derivatives more or less difficult than the original problem?
Less.
A lot less. I'm only differentiating one thing at a time. So when I differentiate both sides, I d dx both sides. There's my left side, like always. But what's my right side? What goes here? F prime. Here, g prime. Here, h prime. And I'm completely finished with the calculus. Did I use any product rules here? No? Ooh. So, what is dy dx? It's y times all of this. Correct? But what's y? Y was f times g times h. Could I have done this for more than 3 functions, by the way?
Yeah.
Is what I'm doing more difficult with more functions, or is it the same?
Not really.
If I added 10 more functions, you just keep going, but it's not harder, I just get more stuff.
Hmm.
But the next thing we write will be the final answer to the problem, whether we had 3 functions or 3,000 functions. If you were differentiating 3 or more functions in a product, you would always want to do the logarithmic. I'm telling you, it'd be significantly easier and faster. When I distribute, what am I going to be left with? G H F prime plus F H G prime plus F G H prime. I'm done. That is the 3-way. If I did 3 functions. What if I had a 4th or a 5th or a 6th or a 7th? You can kind of see an algorithm. No, you're never going to have to worry about that. Don't worry. In this class. Can that happen in other levels, in physics and other? Yeah, yeah. And the thing is you have a technique. I don't want to call it a trick. It's a very specific technique that I take a problem that did not have logarithms. I use the properties of logarithms, namely the log of a product is the sum of the logs, or the log of a quotient is the difference of the logs. And I use that to my advantage. Now, does that mean the problem's going to be easy? No, but it's very likely to be less work and certainly less algebra. Now, we did problems of this nature a few lectures ago. Do you remember what the worst one was, though? I think we had a quotient and we had roots. Ugh. I don't want the answer so much as the setup. Let's do one more really terrible one. So how about y equals, how about the square root of 6x cubed minus 4x squared over, I don't know, let's say the cube root of 2x to the 6 minus 6x cubed, and I'm raising that to the 4th power. I don't know, that's pretty hateful. Do we agree this is horrible?
Yeah.
Good, okay, good. I want the derivative. But let's set it up that way. So if I do the log of y, then it's the log of all of this big gobbledygook, right? How about if I rewrite the bottom as 2x to the 6th minus 6x cubed to what power?
4 over 3.
To the positive 4 over 3? And what would I write the top as?
To the 1/2.
To the 1/2. The log of a quotient in English is the
Difference of the logs.
the difference of the logs. I'm not going to skip any steps because I don't want anybody to get lost. I think we all agree the original problem was downright scary. Now what can I do with those exponents? Right? You all know the sound they make. Have we done any calculus yet?
Nope.
No. But we're going to take the derivatives of these two guys. This is the only calculus step in the problem. Now I'm going to differentiate both sides of this with respect to x. So this is not log of a variable, this is log of a function. So it's 1 over the function times derivative of the function. That's why we write it like this. And on the right side, that's, sorry, cube. Okay, and then Now, that 1/2, I'll just put it right here. That 4/3, I'll just put it right here. What goes in the numerator here?
18x squared minus 8x.
18x squared minus 8x. What goes in the numerator here?
12x 5. And 6x squared.
Can I distribute both of these fractions into the numerator? I think I can in both cases. So why don't we do that? Then we get rid of the fractions. So now that would be 9x squared minus 4x over nasty stuff minus, what would that be? 16x to the 5th minus 8x squared. Now this is 1 over y dy dx.
I think your 2's at the very end of your equation are supposed to be 6's. This would be 6x.
Oh, hold on a second, where are we?
So
Did
the
I,
bottom
you're right,
equation,
you're
yeah.
right.
So then
Ah.
those are both supposed to be 6.
That's supposed to be a 6, thank you. So
And so there's a.
where does that
top
one
would
come in? That comes in,
This would be 18x squared.
good catch, good catch. That's a 6, so that's an 18, good. Okay, and then that makes that 24. Yeah, we want to get it right, thank you. Now, this is 1 over y dy dx. What does y equal? I'm sorry, sorry. What does dy dx equal? I'm going to multiply both sides by y. How do I want to represent y? Do I want it with roots or fractional exponents, do you think? What would be easier, do you think?
Fractional.
Probably fractional exponents. So that would be 6x cubed minus 4x squared to the 1/2. And if I write it times, that's not going to hurt anything. 2x to the 6th minus 6x cubed to the negative 4/3. Now, when I distribute here, when I distribute this into here, this is one of them is going to cancel with this guy. And when I distribute this into here, something's going to cancel with this guy, and I'm done. Now, there's still some factoring, there's still some common denominators if you choose. But if we go back and look at how we did this problem last day, that was pretty big and scary. But where did I use the fractional exponents in this problem? I didn't. They became coefficients of the logarithms. So one of the huge benefits to logarithmic differentiation, again, is it takes exponents kind of out of the picture, especially when I have functions raised to powers. Do you ever have to use this as a method of doing a problem? No, but there are many times it will make the problem way simpler, way simpler. Okay, I'm going to give you an example of one right now. Last day we did some implicit differentiation problems involving exponentials and things, and could get kind of hairy at times. So what if we have something like this? I've got, how about e to the y minus y squared e to the x, I don't know, equals, how about 3? We're going to see that later. But basically, we agree that sine and cosine stay between -1 and 1. But the tangent can produce any real number. So if you do inverse tangent of any real number, you will get an answer back again. All right, so do the inverse tangent of 1. Start with an easy one. Inverse tan of 1. It's 45 degrees or pi over 4 radians. I would always use degree mode first, because then if it's a common angle, I can easily convert it to radians. But does anyone here recognize the decimal equivalent of pi over 4? Yeah, probably not. Right? That's not something you see. If you saw pi on your screen, is it likely you'd recognize it? It's likely you would recognize it. You know, okay, 3.14, so okay, yeah, that looks like pi. But any version of that, any multiple, any fraction of that, probably not going to recognize. That's why it's easier if you're in degree mode for the purposes of figuring out where you are, and then always take the degree answer and converting it back. So if I do the inverse tangent of any angle, I will get back, excuse me, any ratio, I'll get back an angle between negative pi over 2 and pi over 2. That makes things very, very practical. So let's do an exercise. I'm going to go way back. I subbed for a trig class multiple times already this semester, and we were doing this on the 3rd or 4th day of class already. So this is how early you started this process. All right? I'm going to tell you that the sine of theta, use theta as my angle, is, let's say, 3/5. I want you to find for me, how about the cos theta, the tangent of theta, the secant of theta, the cotangent of theta, the cosecant of theta. Now, there's one other thing I need to tell you. What quadrant I'm in. Because the sine is positive in both the first and the second quadrants, but not all the other guys are. So I want the sine of theta to be 3/5, and theta is in the second quadrant. Now, you guys have all done this. I'm going to walk you through how you did it again. You're going to go, oh, yeah. That one really didn't give me too much trouble. The best part about this, I never actually need to find the angle. Because my answer is not the angle, my answer is the cosine of the angle. So what I'm going to do is draw a picture, not a unit circle. You can always do a unit circle, but now you're dealing with icky quotients all over the place. I'll just draw a simple SOHCAHTOA picture. I'm in the second quadrant. Okay. Can you draw me a picture, your right angle, where the sine of this angle is 3/5?
The y would be 3.
Where's
and
the 5?
The 5 would be the r, just the diagonal.
So what would this be? Would that be positive or negative?
Negative.
Negative. How would I find this value?
-4.
So in other words, you're saying negative, this is going to be negative something, comma 3. Well, if I use Pythagorean theorem, what's that other side?
-4.
Negative 4?
Yeah.
Whether you put the -4 here or you put -4 here, I don't really care. Is this triangle representative of the question? All right, can you tell me the answer to each of these without doing a whole lot of suffering here? All right, what is the cosine?
-4 over 5.
Okay, what's the tangent?
3 over -3/4.
What's the secant?
The inverse of the cosine.
Yeah, -5 over 4.
It's not the inverse.
Sorry, the reciprocal.
Yeah, no, that's one that, my hackles right, yeah. If you mean inverse, say inverse. If you mean reciprocal, say reciprocal. There is never going to be a time the rest of your life. I'm not joking. There is never going to be a time when you're going to get the same answer. In fact, one's an input, one's an output. That's how far apart they are. One's an input, one's an output. They're never going to be the same thing. All right, this is the reciprocal of which one?
The cosine.
Cosine.
Reciprocal of the tangent. And then the reciprocal of the sine.
Did you have to ever find the angle?
No.
Why was the quadrant important?
The negatives.
Yeah, the plus or minuses would have been different if I'd been in a different quadrant. Was that hard? Probably not. Do you guys remember doing something like that at some point in your lives? Yeah, that was pretty simple. That wasn't bad at all. All right. It's the being able to work through this is really, really important. So now I'm going to do a slightly higher level one. I want the cosine of the inverse tangent of 4/7. Is my answer an angle or is my answer a ratio?
Ratio. Yeah. Wait.
This is actually the same as this question. I asked it differently, but it's really the same problem. In this question here, I asked you all of these things, but what I was really asking you to do is find the cosine of the inverse sine of 3/5. That's what this is. This is the tangent of the inverse sine, and so on and so on and so on. Okay? Now, I don't need to tell you the quadrant because the inverse tangent, it's automatic. Inverse tan returns which two quadrants?
1 and 2. Or 1 and 4.
1 and 4. when is the tangent, the inverse tan of this ratio produces an angle, but the ratio is positive, so which quadrant must it be in? First. If this had been negative, then I would have had to be in the fourth quadrant. This is how you determine quadrants now, by the plus or minus, okay? So no matter what, my angle is in the first quadrant. So I'm gonna draw a picture there. Now, this is your theta. Inverse tangent of a ratio is producing the angle. That's my theta. Would it be correct to say then that the tangent of theta equals 4/7? Is that a correct statement then? What do you think? Yes?
Mhm.
Yes. That, by the way, it's huge that I see that, because now you see, oh, it really is the same question as this one. Why do I need that? Because I need the picture. I need the appropriate picture. So what goes where?
Seven's the bottom, and then 4 is the right side.
Because the tangent is the ratio, right? This is the TOA. And then what's going to go here?
Root 65.
So 49 plus 16, 65, so the square root of 65. Everybody cool with that? I haven't answered the question yet, but everything I need is right in front of me. I now need the cosine of this angle. What would the cosine be?
7 over root 65.
7 over root 65. Beautiful. Oh, here. Is it possible I made a mistake? Is it possible you made? It's always possible you made a mistake. Can I check this? When I do this on my calculator, I'm never going to see that number. I'm going to see decimal equivalents. But can I compare decimal equivalents? Yeah, so what I would do on my calculator, literally from left to right, type in cosine tan inverse 4/7. And you're going to see a decimal on your screen. So everyone do that for a moment. Do the cosine of the inverse tan of 4/7 and tell me what decimal you see. There's no way in the world you're recognizing this decimal as being anything.
0.86.
Okay, 0.8 equivalent. Okay, so just remember the first couple decimals. All right, now do, on your calculator, do 7 divided by root 65. I'm showing you the ultimate lazy here.
Basically the same.
Is it exactly the same? You didn't memorize the whole thing, but you remember the first couple places. Are they the same?
Yes.
Yeah.
Yeah.
Is there any possibility it's wrong? No. None of them are the same. Well, you know, they're almost the same. No, they are the same or they're not the same. They're not almost the same. So I just gave you a quick check. The problem with doing this directly on my calculator, all I'm going to get is a decimal equivalent. I'm not going to get that, and that's the answer I want, but I can check using my calculator, using the inverse key. Does it matter whether I'm in degree or radian mode? No, because I never asked for the angle. I only asked for the ratio, and the ratio is the same regardless if I'm in degrees or radians. So that's sort of a little safety net there. You like that? Yeah.
Would you want us to take the square root out of the denominator? Would you?
For what reason?
Just, I don't know, my pre-calc teacher used to do that.
No, actually, that's the most, well, I'm glad you brought that up. That's not really it's less of a thing in this class as it is in the higher classes, because in Calc 3 they deal with vectors and they have to deal with unit vectors, so the answer to every question has roots in the denominator. And I'll go out on a limb and say probably everybody in the room was told wrong information. And I'm not saying that jokingly. It's reasonable that everybody here learned it incorrectly because of one simple vocab word that most people don't even know what it means, the term rationalize. This is the right question to ask, because the question often is, am I done? Do I need to keep going? The only real rule when you have a quotient is that you've reduced as far as you can reduce. There are no common factors left. Do we agree with that? No one would write a final answer, 4 divided by 8, because I can keep going. But if my answer was 4 divided by 9, there's nowhere to go, so I'd leave that. If I needed a decimal approximation, depending on the class, I can always give a decimal. That's not the question. The question is, when roots are involved, how far do you take it? So, let me ask you a question. You just did the cosine of pi over 4, or 45 degrees. You got that. Somebody else gives me that. Somebody else gives me that. Tell me about these three answers.
The same.
They're all exactly the same answer. You've been told all your life you're supposed to rationalize. I'm guessing no one actually has ever in their entire life rationalized. Because only one of these is rationalized, and it's the only one no one ever is going to use. There's only one that's rationalized. Anybody know which one it is?
Third one?
The third one. The term rationalized means there's no root in the quotient. It has nothing to do whether it's numerator or denominator. You can't have a root in the quotient if it's rationalized. The reason you learned rationalization is kind of archaic now. Okay, how many have had an algebra course recent enough that you actually remember something about it? Like when you looked in the back of the book, it had a table of logarithms and a table of square roots. You guys remember that? It'd give you like 5 decimal approximations of both roots and radical logs from 1 to 100. Because these books were written before the days that handheld calculators were